Very good. Okay, good. So today we will continue to talk the probability theory, and also we will touch upon on a very classical example in the statistical mechanics. It's called random walk. Okay. So before that, a few logistical updates. Firstly, we have the homework number 1 uploaded, and then I think I saw you guys did very well in the homework number 1. Also, the midterm exam number 1, also you guys did great, excellent. So both of them actually, you don't have any issue. Now I also put the homework number 2 on. So this homework, you will need to use the MATLAB. I have very detailed instruction in the homework number 2 about how to do each step. So you make sure that you read that very carefully. All the needed information are in the problem sheet. Okay. So previously, when we in our previous semesters, the students actually don't need to ask any question once they get the homework number 2 sheet. So that problem sheet and the tutorial are sufficient for them to complete the problems. Okay. So I think, I think this is a very good opportunity for you to practice how to use MATLAB tool and how to simulate the random walk and understand the probability theory in a deeper manner. Okay. Now, after the homework number 2, we will have midterm exam number 2. For the midterm exam number 2, as we explained in the first class, it will be linked to the final project. So final project, you will present a research project that use that need to be deeper and quantitative. Right? Midterm exam number 2 is actually a chance for you to present the topics and backgrounds that you plan to work on for the project. Okay, so you can, this is an opportunity for you to examine whether the topics you selected is appropriate or not, is interesting or not, is useful or not. Okay, so that is a midterm exam number 2. And then this after the midterm exam number 2, you can go deeper, propose modeling or propose new experiments to study that, and then work on that to make the project deeper. Okay, so this exam can be either individually, so any one of you can select a topic, or can be collaborative. Several of you can work together on a project. Some of you actually talked with me already. So the two students work together. I feel that's very good collaboration, theoretical and different background, the physics background and biology background, work together on an interesting project. That is excellent. That is ideal topic. That is ideal types of topic you can work on. Okay, so you can either way is fine. So you can start to prepare that now for the midterm exam number 2. I will announce the date. It should be end of October. I will announce the date. Okay, so then you can present for each group can present for like 10 minutes. Okay, so then and everybody will give you comments and questions so that you can improve the project. After that, you can start to make them deeper and then make them to be the final project. Then you can present it at the early December. So then you get the final score, and then you use that to write a final report. Okay, that's it. So I hope those process will help you to learn how to find out an interesting project, how to develop that project and make it deeper, and then how to present that project to your colleagues. Okay, can you guys hear me?
Yep,
yes,
we hear you.
I can hear you.
Yeah, excellent. Okay, yeah. So, okay, that's midterm exam number 2. For the reading, as I said last time, we have for new readings uploaded on the canvas, and those are on the statistical physics and the Brownian motions. Okay, so feel free to read it. We have an invited lecture on middle October. I will put the dates to be determined, but middle October we will have an invited lecture by Dr. Brent Reynolds. He will talk about something very interesting about the neuron stem cell. As we know, stem cell is actually mechanical sensitive, right? Some of you actually write it in the midterm exam number 1 when we ask the first question, how the mechanics, how the physics force related to the life. Some of you write the stem cell, right? So that's correct. Stem cell actually is a mechanical sensitive, and the mechanical force can actually guide their fate. And one of the stem cell actually existing in the brain, that is neuron stem cell. Those cells will differentiate, choose their fate to the neuron, glia cell, okay, and some other tissue cells in the brain, okay. So Dr. Brent Reynolds is the expert for neuron stem cell as well as the glioblastoma cancer, brain cancer, okay. So he will talk about this and also some new technologies he developed to study those normal physiology and cancer biology. Okay. So this actually is a very important topic. Brain cancer, glioblastoma is actually incurable. There are no good tool to kill those cancers. Okay. So his research is very, very important. After October, about middle November and the end of November, we have 4 other invited lectures. 4 other professors will give a talk on different topics. All of them are very exciting. Biophysics and biology, physiology, integrated topics. So you will learn a lot from those invited topics. Okay. So firstly, let's finish our own material, and then use those material. You can appreciate their work much better. Okay. Okay. So last but not least, for the survey, so make sure that you send me the survey regarding to the question you may have, to the opinions you may have. Okay. Some of you constantly send me the survey. That is excellent. That's great. From those survey I received, it seems you guys are doing really well. But several other of you have never sent me the survey. If you don't have question, that's fine. You don't need to send. But if you have question, feel free to send. Don't be shy. Don't be shy. Okay. Good. Is there any other questions? If no other question, let's start today's lecture. Okay. Now, we will go through some mathematical factors and then calculate the consequence of Brownian motion that we discussed earlier. Okay. The phenomena we discussed earlier. Okay? And then we will learn the macroscopic diffusion and some examples. Those examples have not been well understood previously because of the lack of the knowledge. But now, after you learn the things we will discuss, then you will understand better about those examples, such as what determines the gap between the blood vessel in the tumor and in the tissue, right? So those actually is because of the diffusion of the nutrients. And then diffusion of nutrients actually is a random walk process. That is the same random walk process. That is that shares the same mathematical languages, mathematical principles of Brownian motion. Okay, and then to learn and understand the Brownian motion, we need to know what is the mathematical background of that. So we need to use correct mathematical tools to understand it. Probability distribution is one of the correct tools we need to know. Okay, so let's go through them one by one in a logical way. So first of all, in last lecture we talked about the probability distribution, right? So consider that there's a particle, okay, that takes steps in one dimension, in one direction around the x-axis. And when they take steps, the step is called S, okay? S step. And now take 1, 2, 3, 4, many steps. The step identity which step is the subscript I, which step? The step I is the SI, okay? Step 1 is S1, step 2 is S2, okay? Step I is SI. This step, each step, they have the size. The size of the step follows a distribution. That distribution is called WS, okay? This distribution gives the probability of any step this particle takes. What's their size? What's the step size? Because direction or the direction or the route is the same. They're always 1D, okay? Can be positive or negative x, but it's always 1D, okay? So that is only the step size determines where is the particle after it takes many steps, right? For each step, it follows the probability distribution WS that is shown on the right hand side. So the x-axis here shows the steps size. It can be 0. It can take a step, but that step is on the same location, so that the step size is 0. The is still stay in the same position. Or step size can be 1, and then the corresponding probability is actually is 0.7, around 0.7. Okay, and then for the particle to take a more larger steps like 2, 3, 4, the probability goes down because the particle has a certain limitation. It cannot take a very large step. Okay, it prefers to take the step size at the small level, small size. Okay, then all this probability, actually this is called probability density. Okay, all this probability density integrated together as a function of the size, then finally it gives the value 1. That 1 actually means 100%. So it means all the possible step size and their corresponding possibility is accounted. Okay, so for each one step you have 100% chance. Okay, so to make it happen. Okay, so this can be summarized into one equation, that is the integration. Okay, so overall 100% possibility for that one step. Overall, it can be integrated together. So that is the integration of probability density, or you call it probability distribution. Probability distribution times all the possible step size, of S. Okay, this S from minus infinity to positive infinity. Okay, then they integrate together equal to 1. Okay, so that's actually the mathematical expression of this one step, and this actually is the meaning of the probability density. Now, this probability density WS, it is a distribution. This distribution implies the size distribution of this particle in this condition. And then this distribution actually has its mean value. Its mean value means what's the value if you take many steps, what's the value it most like will happen. Okay, mean value. And then it also has the variance. Means it will not be always happen in that mean value, right? It will be positive, larger than mean value, or smaller than mean value. It will change. It will vary, right? That is called a variance. Okay, both mean and variance actually has a mathematical definition that we show in next slides. Now, if we look into this deeper, let's consider a function. So let's consider a function or a quantity that is defined by a function called fs. This is a function fs. This f is a function. S is the variable inside. S, the step, means that you take some step and then take a step. Each step can be added into a function f, and then that will yield a value. That value is this quantity, okay, called fs. This quantity, if it's dependent on the step, then after many steps, what's this value? We want to know what's this value. If after many s, that value actually can be written in the way as f in the bracket. This value is called expectation value of f. Okay, expectation of value of f. So this function is an expected value because this f is dependent on the s, and s is a distribution, right? So then based on that s distribution, what is this f value generally? Okay, so then this value actually can also be written in using this probability distribution equation. So it actually, this expected value equal to f function times distribution, probability distribution of the s, and then times ds. ds is from -infinity to +infinity. So when you do this integration, this fs, this function associate with its corresponding probability distribution, and then integrated throughout all the possible value that s can happen, then gives the final expectation value of f. Okay, and also remember here we have normalized all the probability distribution, right? It equals to 1. So that then it by multiply this one to the f, it will not amplify f or shrink the f. It will just find out which value is the final mean value of the f, right? Do you guys see my mouse? Yeah. Okay, very good. This is a very important concept. You will see that it start to change now, start to get more different. You get into different conditions now. Okay, so you need to really understand what does those mathematical terms mean. Okay. Now, this physical meaning, as we said, the physical meaning of this expectation value actually is we repeatedly select many s from based on their distribution ws. For each s, it will follow a distribution, right? For each s, and then from this s, we can put it into the function fs, and then we can calculate fs, and then that means there are many fs, right? Fs is also a distribution now, and then this distribution fs actually we can integrate them together, and then get the average value over all those different s, and then we can get the expectation value of fs. Okay, so this bracket symbol is very important. Bracket symbol in the statistical mechanics, it is used to tell us what's the mean value of a function. Okay, and that mean value is the value that we can use to know what's the most common phenomenon that yield by this function. Okay? Now, for the mean and variance, they have a specific definition. If we still look at that probability distribution ws, take the steps. The step is s, as we said. This step s has many different possibilities of the step size. Now, what is the average step size? If you take many of them, but what is the average step size? Okay, what's the most possible step size? This condition we give, right? So that s also you can take put the bracket around the s. Then that is the s bracket. This value actually it means the mean of the s. Okay, this mean of s is actually s. This s replace previous f function. S times probability distribution times ds, and then do the integration for all the possible s. Okay? So this s inside, and then this s inside will give the s in a bracket, and this value always we use mu to represent it. So mu is the mean of a distribution of s. So this actually can be represented here. Mean is here. Mean is the center. If we do the calculation, okay, mean is the center, and the ws is actually the curve of this function. S is the x-axis, different values. Okay? So that's the mean. And as we said, the s will not be always in the mean. It is just the most probably on the mean point. It also varies above or below mean, right? That variance is called variance. That is quantified by the variance, and that variance is mathematically defined as s minus the mean, and then take the square, because it can be positive or negative. You want to know what the absolute variance there. So then you have s minus mu square, and then take the bracket, means take the mean value. Take the mean value of this value. The value is s minus mu square. Take this value. Okay. So then by now, when you look at this, you know what to do now, right? You know this actually is we use this one to replace the fx. So we put this one inside the integral. So this value times ws times ds, and then do the integration, right? Now you also will know this actually has different unit, because it has square. Unit is different. Okay, so this variance we usually use sigma square to denote it, and this square means sigma has the same unit as mu, but sigma square is a square. The unit is a square compared to the mu, right? So and the sigma actually is called standard deviation. So standard deviation is the square root of the variance. Okay. So let's calculate this one. So this one, to calculate this, s minus mu square equals to this s square minus 2s mu plus mu square, right? We know this. And then times ws times ds. Now, first term, s square, this is a positive value, right? S square, if we separate that, s square, so here follow me closely. S square times ws times ds, that is one value. This term, what does this mean? S square times ws times ds. This actually is the s square's mean value, right? So then it's s square, take a bracket, right? Now second term is in the integration you have minus 2s mu times ws times ds. Minus 2s mu. Mu is a constant. That depends on this s. Is a constant. S is not. S is a varying, and you have ds. So you have a minus 2 mu constant. Take out of the integration, and s inside times ws times ds. S w ds is this term. It's get another mu, and then combining with the outside is minus 2 mu times mu, means minus 2 mu square. Second term. Third term is mu square times ws ds, and then mu square is constant. Take it out, and then you have an integration of ws ds. Remember, we have said this is normalized. Ws ds times get the integration equal to 1. So then you only have the outside constant mu square times 1. So then second term and third term actually is minus 2 mu square plus mu square, means minus 1 mu square. So that's actually this term, minus mu square. Do you guys follow me?
Yeah.
I think I followed you.
Excellent. So minus mu square, mu is what? Mu is s average. So that is actually here, this term is the minus s square, s average square, right? So this term means the variance. This is variance, and you make sure differentiate these two. This one is do the square in first, and then take the average. This one is take average first, and then do the square, right? So this is two different terms, and this is a positive definite, okay? Can be zero, but always either positive or equal to zero. The reason is S can be positive and negative. If you square it, then the average is always positive. But here, S is average together. S can be negative and positive. This average value can be zero, or can be zero, or can be smaller, right? And then take the square. This term is smaller than this term, always smaller than this term. Okay? So variance means variance is always positive. So there shouldn't be negative value. Okay? Now, these two are most used. Mean and variance is most used two quantity that you need to understand any distribution. For any distribution, whatever the distribution function is, WS can be anything. It can be Gaussian distribution or not Gaussian distribution, doesn't matter. But any distribution, they will have mean and variance, and those two are the most important. For the Gaussian distribution, that is also called a normal distribution, the mean is mu is here, and the variance take square root become standard deviation. Then it actually is it demonstrates how wide distribution, how widely the distribution can expand around the mean, right? For the Gaussian distribution, sigma is a sigma plus minus sigma. First sigma is actually 34.1%, means within the variance, positive and negative together, this middle part surrounding the mean, you have almost 70%. So almost 70% of chance the particle are inside this. Okay, and then you go even further, 2 epsilon or 3 epsilon, you get less and less. Okay, so that's Gaussian distribution, very important. Now you can also let this go up even more. For example, third order, we can have S minus mu cube, take the average. Okay, and also fourth order, S minus mu, fourth order, take an average. That's also fine. These two also has a useful meaning. Third one is called skewness. Fourth one is kurtosis. These two mainly in the mathematics, they are very useful. But in the physics, in the nature physics, these two are very rarely used. Mainly is the first order and the second order. Okay? So in our class, so far, let's stick to these two. Now, as we said, at f function can be any function. F function can be any function. There's one very special function. It's called a delta function. So that delta function means the probability distribution is not distributed. It's actually only at one point. Only has one value. Only has a value. So then that is called the probability density function is actually a singular value. People use delta x minus a to represent that. X is variable. A is that value. Is that value that single step will recite. Okay, only that value. So x minus a. When the x equal to a, then you get a delta zero. Delta zero means that value is infinitely large. So you can see the distribution here. Now it only has the step size at a, right? And that value is a line. This line actually go infinitely large. But outside this value, non-A region, everything is zero. Okay, everything is zero. So this use the x minus a to denote it. Now this one is WS. This is WS. If this WS, we do the normalization, then this WS times dx. X means S, right? All the possible step size. This do the integration will equal to 100%. Okay, so it means integrate this guy together is 100%. Okay, so here even this in terms of the area, even this point is very small, but it's infinitely long, infinitely large. So then this very large thing times very small thing together they equal to 1. Okay. Now, if we use this distribution, the average value of this distribution, then we put the x, to calculate that, we put the x in, x times this distribution, dx. This one is mathematically correct. If x in, then they do this integration. Here, it only happens when the x equal to a, okay? You have value. And then that x equal to a times x equal to a. This x become a. And then this x equal to a times dx. This term equal to 1, showing here, equal to 1. Then the final results, mean equal to a, okay? So the mean value is a. Now, for the variance of this, you calculate this variance equal to 0, because there are nothing outside this mean value, is 0, okay? And for any other function fx, if you wanted to know the expectation value of fx, then you put the fx in times delta x minus a. You do this one, because in this function x, the term becomes 0 when the x is not equal to a. So only x equal to a has this value. So then only value left here is fa times 1. So eventually get a fa. Okay. So this is a very important, very special probability distribution function. Okay, but even is very special, it occurs in the nature. For example, if you remember, I said Galton that the ball, many balls coming out, falling down from the center, and then they bump to the horizontal pin, and then make a decision, go left or right, right? That step, that decision make step, each step, in fact, the ball falling down to it, and then go to the left or right, they actually can only, for example, here on the right hand side, when they go, they can only go here, only go in this location or this location. That means the distribution for the ball to take any step downwards, any step, that step is a distribution function. That distribution function consists of two delta functions. Okay, and then this distribution will repeat many times as the ball going down. Each time they will take this distribution. Okay, and then that distribution can be written as a half right side. Here delta x minus L. So x has to be equal to L to make this happen. X equal to L. Okay, then you have delta 0. That means it's this right hand side. Half 50% right hand side, 50% right hand side, one half delta x minus L. And then another 50% left hand side is a delta x plus L. So as x equals to negative L, then this one equals to infinity. Okay. So this is the distribution. Now this one, if you put that into the calculation we used before, calculate the mean and the variance. If you have this expression, you will find mean equal to 0. Mean equal to 0. Okay, you can calculate it, put it into this equation, put that 2 into replace fx, then you will find the mean equal to 0. Okay, if you calculate the variance, this variance actually equal to L squared, because now it's not the whole distribution. Is surrounding the mean 0. So then it's a positive is L, negative is L, right? So and then you will find that it's actually variance equal to L squared. Those can be calculated using this distribution function. Okay. Now, do you guys follow me? Yeah. Good. So once you understand this, now we can look into the exact example. So here's one example. Imagine a person that is drunk. Okay, so this is a random walk. This is called random walk. So imagine a drunk person. Okay, or some you can also is a same as a tiny particle. Remember when we see the video Brownian motion, tiny pollen in the water, they will move in a random way because they have no energy for it. There are no free energy for it, so they cannot work in like a motor protein. So their working is depending on the random bump from the water molecules. So it's going in non-directionally. Okay, no free energy there. So either case, our goal here is to find out the underneath principle to characterize any characteristics of this random walk process we can learn, because this happens so many times in the cell. In the cell, if the molecule has no energy to be supplied, then it also do the Brownian motion, do the random walk, right? So if in a bacteria that you have one protein generated by the cell from the ER now, then this protein generated in the ER, it is supposed to go to another location, such as go to the membrane of the cell, because that is a protein membrane, a membrane protein. You need to go to there, but there are no energy to supply to this protein to let it go, and no motor protein want to do this job. Then the default option for that protein to move to the membrane is to do the Brownian motion. Then that protein is assigned as a drunk person or a pollen in the water, right? They do randomly until they touch the membrane, right? So we want to know how long it takes, how long that time takes, and then during that way, what is the characteristic trajectory of that protein, right? So to understand that, we need to do some mathematical derivations. First, the question we want to ask is, after this protein or this tiny particle or this strong person, after they take those steps, all the steps are random walk. Every step is step 1 and step 2 is not correlated. Those steps, every step is independent, right? Because the person is drunk, he or she will not remember what he or she did in the previous second, but already forgotten. Okay, so every step is non-correlated, but those steps is in succession, right? One after another. So after n steps, what's the position? After n steps, what's the current position? That's what we want to know. If that position is enough far away, how far is that? We want to know that. Okay. So to calculate that, we can denote that position, final position, as x. That is after the particle. Let's see particle. Okay, but the drunk person is the same. That particle has taken n steps. Okay, then that position x, if we see this is the positive and negative in 1D, okay, one dimension, that x final position actually equal to sj. S is a step, can be positive or negative. J is the number, the step identity, which step, okay? And then that step is from 1 to n, 1, 2, 3, up to the n. And then add all those steps together, can be positive or negative, okay? And also they follow the probability distribution WS, okay? So then they summarize all the S together. Then you have the final position X, right? We have that. Now, if we do this, the X value, if we take the mean, what's the mean X? Okay, we take the mean of X. Then it means that we also take the mean of this summary, mean of this summary. And then mean of this summary, this S is all added together. It's not multiplied, it's adding together. Then we can take this summary symbol outside. So it's equal to summarizing, adding all the mean value of each S together. And then each S, the mean, they all follow that WS, right? They all follow that WS. So if you take the mean of each S, the mean is actually equal to mu, and the mean value. And then you have J equal to 1 to n, means totally n times mu. Then you get n mu. What does this mean? This means the mean, if this x value, the mean value of x, that x is consisting of a series of s. and each s as the mean mu. A series means n number, okay? And then the mean of this guy, mean of x, equals to step number times the mean of each step. Mean of each step, okay? So the mean value of x is proportional to the number of the step it takes. More step you take, even this random, more step you take, the mean value is also larger. Means the person is always further away from the original point. Okay, and this is linearly proportional to that step number. Okay, so this is first very important derivation. First, very important. Second one is we also are interested in the variance, right? So to calculate the variance is the position, final position of that particle x minus the mean, right? Mean. Now we already know the mean. Mean is n mu. We calculate that, and then take the square, and then take the bracket. Bracket means we multiply with the ws and then ds, and then do the integration, right? Take the mean value, but use the bracket is simpler, right? So now this value, this is the variance of future of the final x. That means this x is also a distribution, right? This x is also a distribution. So this value, if you look inside, x minus n mu times square. That what does that value mean? This is the mean value. X is the variable there. This actually means delta x, right? Delta x squared, right? Net change, right? Delta, because this is the s final position with respect to the mean value, right? So that's the delta x. So this delta x squared, take the mean. This one, if we put the expression of x in, then it's a summary of all steps, add in, minus n mu square, take the mean, right? And then here you have n mu. Here you have n step. If you take each step minus mu is actually the mean of each step distribution, right? So then n value of step minus n value of mu, then you can actually rearrange it into n terms added together. Each term is the step minus mu. Then you get a delta, net change delta sj, summing together n delta xj, and then take the square, take the average, right? Good. Now here, once we have this, that right now you have one term now. One term have many summary now. One term, but one term has a square. That means two. This summary of delta s multiplied together. Each one contains the n delta sj, right? Then we multiply them together. So two of them multiply together. Then you can have delta sj or multiply with delta sk. K also from 1 to n. J also 1 to n. Means every term in the sj will multiply. Every delta sj will multiply with another delta sk. That k is from 1 to n. Okay, you times everyone, and then sj j go to another value. That value is within 1 to n. Another value. That value also times all the delta sk. Okay, that can be represented by this mathematical representation, right? So here you have the most explicit expression of the step delta step change. Okay, now here, based on this mathematical expression, we can find that there are two groups of terms within this term. This term, how many terms? N times n squared terms summing together. All those terms, there are two different types. First type is each term. In each term, j and k are equal to each other. J and k are equal. Then that means delta sj equal to delta sk because they are the same term. Okay. Another one is j and k are not equal, such as j is 1, k is 2. Then the delta s1 times delta s1 times delta s2 is two different terms. And every term as we said, they are uncorrelated, not correlated, right? People already forget the previous history. They are not correlated. So every delta S, you actually pick up one value from the distribution. So delta S1 and delta S2, they are not related to each other. But for the first case, delta S1 times delta S1, that is one term times itself. Then it is delta S1 squared. They know each other. They are the same. Okay. So based on this, in these two conditions, they give totally different results within this final this term. Okay. So we can rewrite it. That variance. We can rewrite that variance into one term that is j and k equal. Then you have a j and k. K can be written as j equal, and then it's also j equal to 1 to n. Another one is j and k not equal. They summing together, but they are not equal, right? So here you have n terms. Here, well, how many terms? Here you actually have a n squared minus n. Because total you have a n squared term, and here you already take n terms. So this is n squared minus n terms. Okay. Now, if we have many of those the terms inside, and j and k, they are not related to each other. They are random, not related to each other. Then, if you average all of them together, you sum them all of them together, they actually, this term can be rewritten as because they are not correlated. So then this term can be written as separated together, separated into first delta Sj average, and delta Sk average. You can write it separated into these two. And then delta Sj, remember this is the net change, S minus mu now, right? S minus mu. Then it can be positive and negative, positive and negative. And the net is equal to 0. Okay, net change is 0. Then this term is 0. This net change also 0, because many of them added together can positive or negative added all together. So then this term finally gives 0. Means this term is 0. This one is 0. Okay? So only one term left. That term actually has the delta Sj squared, take the average, right? So then the variance, this variance equals to delta Sj squared added together, and then take the average. And then this here, everyone is the same. Everyone is the same. Because everyone follows the same WS. Then you have n delta Sj squared. That n can be taken out. And then you only have delta Sj squared. What is delta Sj squared? Delta Sj squared actually is the square. This term is the variance of step distribution. Step that WS distributions variance. That variance. That is the sigma squared, right? So then this one finally give n sigma squared. This is the very important derivation. What this means is for the final position, which is also a distribution, that final position is that distribution is a variance. That variance is actually proportional to the variance of each step, proportional to each step, and that proportional coefficient is also the n number, the step number. How many steps you take? Times each step's variance equals to the final distribution's variance. Okay, so in one sentence, variance is proportional to n. Then you combine with previous slides, you will know that both mean and variance of a distribution that consists of n steps together actually is grows linearly with the n number. Okay. Now that is super important. Okay, that's super important. If we stay in the context of random walk, the mean actually has the unit of length step, right? Length, and then the variance is length squared that we discussed. And then normally people use standard deviation sigma to make sure that the unit is physically correct, because length is more physically accurate. Length square is mathematically used, but physically we rarely use that. So usually the standard deviation is square root. The delta x squared, take the mean, okay? And then remember this value is n sigma square, right? So that is actually square root of n and then sigma. So square root of n is no unit, n is a number. Sigma is the unit length. So then this term is people use that for this sigma is actually every step is a standard deviation, and then times delta square root of n, then you get a final standard deviation of the x of the final step, final position. Okay. So far, the things we derived actually gives a factor that is extremely important when we consider any physical phenomenon that can be written or can be generated as the sum of many random contributions. If any phenomenon, we only look at the final product, but that final product maybe is generated by many random contributions. And if that contribution, each contribution, you know their mean and you know their variance, by that, based on the number of that contribution added together, you will know the mean and the variance of final product. Okay, so that is super important. Yeah, and we already show the Gaussian distribution here, right? So okay, now okay, right now it's 3:53. I can stop here and we can continue next lecture. And now we are going to use the thing we derived to understand better how the random walk happens, and then how that random walk is and use that you can explain the pollen, the Brownian motion in the water observed by Dr. Brown. Now you can characterize that, and then from that motion, then people find the characteristics derived actually matches with the hypothesis that the particle, the pollen, is driven by the water molecules bumping. Okay, so that's actually why we said that Brownian motion is the first important experiment that proves molecules, water molecules, indeed exist, and it links macro scale observation to the micro or nano scale world. Okay, so based on that, that phenomenon is that link is theoretically proved without real observation of the molecule. At that time, people cannot have a microscope to see the water molecule, but based on the theory, based on Brownian motion, then you can derive indeed the causal factor is due to the water molecules. And what's the size of water molecule? What's their dynamics? This can be theoretically derived. Okay, good, very good. Let's stop here and we can continue in next lecture. You guys hear me?